You guys don't mind, right? Okay, so the next thing we're going to do is, what do you do when none of the integration techniques work, basically? So, you know, it's all of the problems we've been doing, well, they're made up to work. But in real life, you can't always predict what a function is going to be. So you can't just assume that it's going to be one that you can integrate by hand. So in that case, then we have to make use of computers and their power. So we're going to take a look at numerical integration. And this is actually, in your book, it's 7.1. But I don't really like going over it in the beginning because I think it makes more sense to look at it in the end. After you've seen what you can do by hand, then you learn how to do it when all else fails. Numerical integration. Okay, so let's do first a review. You guys actually already know or should know 3 methods of numerical integration. Before you took this class, you should know 3 methods. What are they? Which one? No, that's for finding roots.
Left hand.
Yeah, left hand Riemann sum. Right hand Riemann sum. Midpoint. Okay. All right. So all the Riemann sums. Okay. So, all right. So let's draw some pictures. So we have, let's do left hand approximation. And so remember the integral, graphically, what does it represent?
It's the area underneath the function.
Area underneath the curve. Okay, so right and then midpoint. Okay, so let's draw a picture here. Let's say we have a function. So the left hand, so let's say we're trying to find the integral from a to b of f of x dx. So we're trying to find the area under the curve right there, right? So we're trying to find that. So the left-hand approximation said, okay, so you grab, so starting from the left, you split this up into several sections. We'll do that many. And it looks like this, right? So here we have 4 intervals. And so, let me see. Okay, let me move this down. I need a little bit more room. Okay, so then we say that this integral is approximately equal to the sum from 0 to n minus 1 of so this is x sub 0, x sub 1, x sub 2. See how much you guys remember. Well, there is a delta x in there, yes. But there's a lot of stuff missing right there. What is it? You're adding up, so you're basically adding up all of these rectangles, right? So how do you get the area of a rectangle? Width times the height, yes, okay. So the height is given by hint, all the values of the function, right? So that's labeled as f of x sub I. So this is f of x sub I times the width, which is labeled as delta x, right? So delta x, remember, is the width, so that's b minus a over n. So the end minus the beginning over how many intervals you have, right? Yes? You guys remember this? Roughly, at least? Okay, so this gives you an approximation of the area underneath the curve, and then of course if you get infinitely many, then that gives you the the exact area underneath the curve, which is defined as the integral of the function from a to b. Okay, but obviously it's not the exact area because, well, you've gone over right there, for example, right? Quite a bit. You guys agree? In that picture? Okay, so let's see here. Now, if I'm going to do a right approximation, I'm wondering, should I do it on the same one? No. Okay, let's do another little mini picture. So we'll do the same picture, but we'll do, so A, B, we'll do the same 4 steps, but this time it's the right-hand approximation. So we go up and then back. Now these are supposed to be straight-sided, but obviously, wow, I think that's the worst. Those are the worst triangles I have, even for me. That's a stretch. Oh, shoot. Wow. I think it's the angle of the tablet.
Blame the tablet.
I know. It's so easy to blame the tablet. It can't fight back. Wow. Okay. Well, actually, it looks worse on here than it does up there. I don't know why. Okay, so x sub 0, x sub 1, x sub 2, x sub 3, x sub 4. Okay, so this is, so the integral from a to b, f of x dx. This is approximately equal to, I'm going to write it down here actually because I don't have enough room. The sum from where to where? What's the difference between the right and the left?
Start over.
Start 1 over, right? So you start at 1 to n, but it's exactly the same thing, right? Okay, so between the right and the left, which one is better, do you guys think?
Same.
They look about the same, right? One goes over, the other one goes under. So then you go, okay, well, why don't we go, so the midpoint, this one is not, you don't go over it in as much, but, so you're going from A to B. So on the midpoint, or basically what you do is you say, okay, well, instead of going instead of starting at the left point or the right point, you're going to just start right in the middle. And your rectangle is going to go to the left and the right. So like you would go up here, and then like that. And then you would go, I guess I should dot them. And then go left. So you go, so on the left, you go, you start at the first point, and then you go right, right, right. On the right-hand approximation, you go up, and then you form your rectangle by going left and left and left. The midpoint, you go in the middle, and then you go halfway left, half right, and then you go down, right? Does that make sense, roughly? So go left, left. Okay. So out of all these, which one do you guys think is better?
Midpoint.
Yeah, midpoint. Okay. All right. So, okay. So we're not going to spend too much time on these because, well, you guys did these last semester. That was so this is a review. So, okay. Now, so using just, so let's forget about the midpoint for now. Let's just take a look at these. Can you, so this one, notice what happens, so if you think about the same function, the left-hand approximation goes, in that picture, it's overestimating, right? The right-hand approximation is underestimating. So an obvious solution would be to average the two, right? Yeah, exactly. Okay, so if you average the two, what ends up happening is graphically, what this looks like is, let's draw it down here. So if you average the two, so that's the most obvious solution, right? Average left and right. So if you do that, all right, so this is what this looks like. So let me so graphically, if you take the average of the two, essentially what you're doing is you're doing this, which are, what are those called? What's that shape?
Oh, trapezoid.
It's a trapezoid, right? That's why it's called the trapezoid rule. Trapezoid. The trapezoid rule. Right? Because you've got this trapezoid right here. So like this right here, this is a trapezoid. Okay, and then how do you find the area of this trapezoid? So what's the base here?
Delta x.
Delta x. Okay. And then how do you find the so let's call, so right here, okay, so notice that I grabbed this first one. So this, what I just drew is, you know, sort of it's this trapezoid right here. So if I label this, let's label these with instead of f of x, let's label these y values. So this would be y sub 0, right? Y sub 1, y sub 2, and so on and so forth. So the height right here would be y 0, and then this one right here would be y1. Okay, so the area of the trapezoid, of one single trapezoid, is equal to what?
1/2 y0 plus y1 plus y1 times delta x.
Yeah, so it's just, yeah, so the width times the average of the two heights, right? So it's, in this case, it's y0 plus y1 over 2, and then that times delta x, right? Does that make sense? So this is this one single trapezoid, right? Okay, so let's derive the formula in general. So let's take a look here. So in general, let's subdivide into n, let's call them n steps. Okay, so like in this example, how many steps do we have?
1, 2, 3, 4.
4, right? 4 subintervals. So we have how many trapezoids? 4 trapezoids. Okay, so let's write this down. So then the area, so the area would equal to the sum of the area of all the trapezoids, right? Okay, so simple idea, right? So let's call it T1 plus T2 plus dot 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 T sub n, right? N trapezoids. In this case, we have 4. Okay, so let's write down the formula for each one of these. So do you agree that, notice how every one of these is going to be multiplied by delta x. So are you guys okay if we factor out that delta x out of the entire thing and just focus on the heights? Okay, so let's do that. So the area is going to be delta x times, okay, so what would be the area of the first trapezoid?
y0 plus y1 over 2.
Okay, y0 plus y1 over 2. Okay. And then, of course, times delta x, but that's why we factor it out, right? Plus, the next one would be, so y1, yep, y1 plus y2 over 2 plus okay, let's see how long we want to do this for. So we want to see the pattern. Plus, So the very last one, what would the very last, let's do the two last one. What would the very last one be?
Y sub n minus 2 plus y sub n minus 1.
Wait, is that second to last or last?
Second to last one.
Oh no, the very last one. The last one.
N minus y sub n minus 1.
Yeah, n minus 1 and then y sub n, right? Does that make sense? So the very last one would be y sub n minus 1 plus y sub n over 2. And so then the one before it would be y sub n minus 2 plus y sub n minus 1 over 2. So far so good? Okay, now, so in simplifying this, what do you guys think? How can I simplify that? What do you notice about all these?
You could factor out a 1/2, yeah.
You can factor out in 1/2. Okay, sure. What else? Let's do it in one step.
Start combining.
So let's say you factor out a 1/2, so you get rid of all those 2's. What else do you notice between all those inside?
There's 2 of each term except for the first and last one.
Exactly. So yeah, there's 2 y1s, 2 y2s, 2 y3s, 2 y4s, 5, 6, 7, 8, until the last one, right? So there's only one of the first one, one of the last one, but all the other ones are, you have 2 of them, each one. So then that means that this would look like, let's see, let's go back here. So this is delta x over 2, and then times y0 plus 2y1 plus 2y2 plus dot dot dot. How many n minus 1s? 2. And then how many y sub n's?
Just
1 y sub n. And that's it. And so this is an approximation for the integral from a to b of f of x dx. Sorry, approximately equal to. Right? Okay, so so any questions?
What was that last term on the end?
In the end. So it's delta x over 2. So if you want to be more accurate, what would you do? What would be the most obvious thing to do?
Make your delta x smaller.
Yeah, so if you're using this method, you make delta x smaller, and then you would obviously have more trapezoids. What do you guys think about this method compared to, well, obviously it's better than the left and the right, right? So obviously it would be better than these two. Do you guys agree? But what do you guys think of it compared to the midpoint method? You would think that it would be better, right? But it turns out actually that the midpoint method is a little bit better than the trapezoid rule. When we come back from the break, we'll talk a little bit about the error, and there's a fun problem on your homework, next homework, related to this. But then also, so check this out, because so trapezoid. So these are sort of not very good methods. Left hand, right hand, not very good. Midpoint rule and trapezoidal rule are like one step above. They're like, that's a lot better than these, but you still leave a lot to be desired, because they don't follow the contours of curvy shapes very well, curvy functions. So check this out. All right, so this is what we're going to do when we come back. Okay, you guys ready? Check this out. This is going to be awesome. Okay. Take a function, right? And I made it especially curvy there. All right, so we go from A to B, right? Okay, so you chop this up into equally spaced intervals. Yes? Okay, so then what you do is instead of approximating it using trapezoids, you approximate it using, this is awesome. This is so awesome you don't even know. That's how awesome it is. You approximate it using parabolas. So every pair of interval has its own quadratic function that goes through those points. This is awesome. So like you have like, imagine sort of something like this. And then you have, so that's one parabola. And then there's, so this one only has two, but you can get the idea. And so you can find the area underneath those parabolas. And since parabolas have more of a waviness to them, then they follow the contours. And the parabolas are made to to approximate the actual curve itself as closely as possible. It's pretty awesome stuff, actually. So that's what we're doing after the break. You guys excited?
Amazingly.
What is it?
Amazingly excited.
Yeah. Okay, so all right, so we've got the idea, right? So one of the important things that we need to bring up is that, so we said that every 3 points we get a parabola, right? So at all these points, so you basically need to have pairs. So like, okay, so like for example, you find the parabola that goes through the first 3 points. So hypothetically, it looks something like this. Now, of course, I'm biased towards making it follow the line a lot closer than it does, but you get the idea, right? So it goes kind of like that, and then the next one follows the next 3 points. So something like that maybe, or so. And then so that's a parabola, and you can easily find the area underneath that curve, right? And then, let's see, so then you've got the next 3 points. And then, I don't know, the next 3 kind of like that or so. Okay, so one of the really important things is that your interval, notice because every parabola goes through basically 2 steps, right? So then that means that you have to have an even number of steps. Does that make sense? So also I want to mention that this derivation is different than the one in, how many of you guys read the book? Okay. All right. So this is different than how the book derives it, but the way the book derives it, it just seems like they grab it out of the air somehow. So this is a lot better because it, see it, you're like, oh, that's awesome. Okay. Well, that's the hope, anyways. Okay. So what we're going to do. So hopefully the idea makes sense. So you grab. So for example, in this case, we have 1, 2, 3, 4 parabolas. We find those parabolas, the area underneath those parabolas, and then add them all up. And so, of course, that seems daunting, but you'll see that it's not as bad as it seems. The first thing that we're going to do, and this will simplify things a lot, is just our curve. We're going to assume that it's centered at the origin. This just simplifies the calculations. And so that it's centered around 0. And we have, so we're going h to one side and then h to the other side. And so what we're going to do is we're going to calculate one of the, we're going to derive it for 1, and then we'll just, kind of like what we did for the trapezoid rule, we'll find 1, and then we'll just add all of them up, and then, then that's it. So, okay, so let's label these first. This is going to be, label this P sub 0, P sub 1, and P sub 2. So P sub 0, what's the point P sub 0? What's the x value? Negative h. And then we'll call the y value y sub 0 to match that P sub 0. Okay, and then the next one is going to be at 0, y sub 1. And then the last point is at h, y sub 1, right? Okay, so, all right, so let's assume, assume,
Y sub 2, Y sub 0.
yes, sorry, y sub 2, I don't know why I wrote y sub 1 there. Okay, so y sub 0, y sub 1, y sub 2. And we're trying to find the parabola. And what's the equation of a parabola in general form? Okay, ax squared plus bx plus c. So assume this function, or this, this function goes through P0, P1, and P2. Okay, and then what are we trying to do? So this is a parabola that goes through these 3 points. So we don't know what it is, right? So these are unknown, but we know that it goes through these points. So if we want to find the area underneath the curve, then we find the area under the parabola is given by, oh, come on, guys, you know this. Yeah, the integral. The integral from where to where? Negative h to h of ax squared plus bx plus c. Okay, now this is a, we're going to get a little clever. Let's say we break this up into the integral from negative h to h of ax squared plus some constant c dx plus the integral from negative h to h of bx. Now you ask, well, why would you do something like that? That doesn't make any sense whatsoever. But what do you notice? Let's take a look at just the bx. What do you notice? Since the interval that you're going around is symmetric, and bx is a, yes, why is it 0? What kind of a function is it? What's it called?
Oh, it's linear.
No. The other one. Yeah, it's an odd function, right? Right? Essentially what you have is, so I mean, it's just, this is a line, right, going through the origin, right? So the interval is symmetric about the origin. So if you draw this, I kind of want to draw it and then erase it. This is what it looks like, right?
The
so the area on the right side, the area on the left side, they're exactly the same, but when you add them up, it equals to 0, right? Because this one's negative, this one's positive.
Right.
So because this one's odd, that one's actually, oh, shoot. This is actually equal to 0, right? Okay, and then on top of that, further simplifying matters. What do you notice about that one? It is even. Yes, it's even. Even, which means that the integral from negative h to h of this function is equal to 2 times the integral from 0 to h. Because it's the same area, right? So instead of just going from negative h to h and doing twice the work, we do half the work and then just, you know, and get the antiderivative and then just go from 0 to h. Yes? Okay. Now, we good so far? All right. Then easily get the antiderivative of that, right? So what is the antiderivative? 2 times ax cubed over 3 plus cx evaluated from 0 to h. Okay. So far so good, right? So what is this equal to? Two-thirds a h cubed, right? Plus c h. 2ch, yes. Oh, there we go.
Minus 0. 0, yeah.
Minus 0. Okay. So what we're trying to do, so you know that's the area underneath the curve. What we're trying to do, let's go back and make sure that we're all on the same picture. What we're trying to do, remember, we're approximating it numerically, right? Which means that what we're able to find is we are able to find the x values at different points, and we're able to find the y values at different points, right? So that's what we have. So what we want to try to do is all that what we just found, we want to somehow relate it to the values that we have here, the y0, y1, and y2, right? So you're trying to sort of mesh those two together. So, okay. So am I able to find those points and relate it to this? How would I do that? So how would I relate it to the polynomial, the parabola? I mean. What do you have? What do you know about the parabola besides from the area of the curve that we just derived? What else do we have? I'll give you a hint. It's on that screen.
What h? The values of h negative h?
Well, no, we have this, right? We have the equation. Right? And so can't we actually find what y0 is in terms of a, b, and c? We can, right? Because so right here, for example, this point is when x is equal to negative h, and then y is y0. So like if you plug in negative h into the x value, this would equal to y0. So like you would have y0 in terms of a, b, and c. And then you can do the same thing for y1 and 0, and then h and y2. And so then you'll have that, and then you can, the hope, and you already know that works because, well, we're going through all this, is that you can match those two up somehow. That's the hope. Okay. All right. So we've got it, right? That's the game that we're trying to play here. All right. So let's go down here back to. Okay. Actually, I need to. Let's do this before we go down and we lose sight of all this stuff. Let's write down. If I plug in negative h into here, then I would plug in y0 into there, right? Okay, so let's do that. So let's write that down. So we have that y0 is equal to a times
A squared.
negative h squared, which is h squared, right? Okay, plus bx, right? So that would be
Minus BH.
minus bh, and then plus c, right? Right, so we just plugged in negative h into the x's, and then y naught at on the left side. Okay, and then can we do the same thing for y1? Y1 just equals to c because the x value is equal to 0, right?
Yeah.
Okay. And then last but certainly not least, y2 is equal to
Plus BH plus C, yeah.
ah squared plus bh plus c. Okay. So now the plan is to get this in terms of the y's. And you can almost see it. What do you notice? If you combine these in a certain way, can you get something that looks kind of like that? Notice how these have BHs and then this one doesn't. Is that a problem? It's not a problem. Why is it not a problem? If you add up y0 and y2, the BHs cancel, right? So you're good there. So that's not a problem. So
We'll take the H out.
so what you're trying to find what combination of these gives you that.
Add y0 once you add it, that one, and then you take the.
Let's let me. All right, so you guys let me know when you see it. I'm gonna try to, maybe I can write it slightly differently. Maybe if I write it like this, ah squared over 3 plus c, right? Something like that. You can almost see it, right? Almost. If you add all three of these, you get that? So let's write this down. So y0 plus y1 plus y2 is equal to 2ah squared plus 3c. So pretty close, right? Close, but not quite. So let's forget about this for now. What can I? Okay, let me do one more thing. If I factor out a 1/3 out of this one, then I would get 2/3 h, and then this would be ah squared plus how many c's? 3c, right? Okay. Very close, right? Can we see it now? What do you guys think? So you can change the number of y0, y1s, and y2s. How many? Of which ones? Done.
Is it always 3 points touching the parabola? It could be 2 or 4.
No, it has to be 3 points, yeah.
No.
Because they come in pairs.
2. Yeah.
Isn't it just the integral? Because it would be.
Well, but there's no reason why you would get the integral at this
Why
point.
they're kind of related like that? Is that kind of what it is?
No, not really. I mean, it's just a the constants here are missing. So okay, all right, one more thing. I'm going to give you one more. Okay, instead of putting the 2 out here, I'm going to put it on the inside. Okay? Okay, here you've got to see it. If I put it in, you guys keep thinking there. Say, so I bring in the 2, and then this becomes a
6.
okay. There it is.
3y1.
No.
So
y0 plus y2 plus 3.
so forget about the h over 3 because that's just a constant. So you're trying to get this to be that.
y0 plus y2 plus 3y1. No. Plus 4y1.
4 y1s, right?
Yeah.
You need
Yeah.
4 y1s, and then you are good to go, right? Because you have this one plus, so y0 plus y2, that gives you the 2ah squared, and then the it would give you 2 c's, and then you need 4 more to get to 6 c's, right? So, okay, so the whole point of this exercise is that, so what we're trying to do is we're trying to find this value, right? The whole point is we're trying to find how do we find that in terms of all the y's, right? That's what we're trying to find. So this, what's inside of the parentheses is equal to y0 plus 4y1 plus 1y2, and then we just multiply it by h over 3, right? Does that make sense? So this is equal to h over 3, and then y0 plus 4y1 plus y2. Okay, all right. So before we write out the whole thing, let's recap what we did, because I think it was lost in translation while we were trying to find those missing numbers. Is we said, okay, so we're going to find the area. So we're going to, find a parabola that goes through these 3 points, and we're going to find the area underneath this parabola. The equation of this parabola is y equals to ax squared plus bx plus c, because we have no idea what a, b, and c are, right? I have no idea what they are. Okay, so we don't know what those constants are, a, b, and c, but we find the area under the curve, right? We find it in terms of a, b, and c, area under the curve, area under the curve. And so we simplify, and we go down, and area under the parabola, area under the parabola, area under the parabola, right? But we still have it in terms of this number a that we have no idea what it is, and this number c that we have just as much of a no idea what it is too. Okay, but then what we do is we try to connect those values, this expression that we have here, somehow to the y values that we are using for our parabola, right? Okay, so then what we said is, okay, well, let's grab the same parabola and plug in the values, the x and the y values, and we have this set of 3 equations, and we're trying to find, okay, well, what combination of those 3 equations gives you this expression that you're looking for? And we found that it was actually that one, right there. H over 3, y0 plus 4y1 plus y2. This right here is exactly that. So these two are the same, right? Okay, so that's for that's for one subinterval. And then the idea is, of course, we'll just extend that to multiple subintervals and just add them all up. Okay, what do you guys think? Before we finish off the formula. Is that pretty awesome or what?
What are we given?
We have, so we would have all we would have is the function itself. So because you have the function, that means that you can always find, given an x value, you can always find the y value, right? Because you have the function, so you can always plug it in and get a y value. So that's all you have, all the y values.
So we'll just have this, for example, the negative h, the y0, the 0, the y1, and the h, the y2, basically for the information given from the original function.
Yes.
Okay.
Yeah, and you get those by plugging them into the actual
Right,
function itself. Yeah.
Okay.
Or it could be, for example, if you're out in the field and you have, you don't have a function, you collect data, right? So you have all these numbers that, could mean anything, and you don't have an actual function. You can't integrate it using any of the techniques that we've learned because, who knows what it is, but you can always integrate it numerically if you have to. Because it's just a set of points, data points. Pretty ingenious, no? Creative, awesome. You add your own adjective as you please. Okay, all right. So, so let's see here. All right, so let's. Yes.
That last purple parabola.
Yes. This one?
No.
Oh, this one.
That right there.
Yes.
That would be going through 3 points.
Yes. I just my skills at drawing are definitely lacking.
Right. Okay.
For sure. That is one of my definite weak points. But yeah, it should go through.
But the middle one doesn't necessarily have to be the apex of the parabola.
No, it doesn't have to be. No, it just has to be a parabola that goes through those points. Yeah, see, cool, right?
Oh, so it's not necessarily exactly, it's still not exact, but it's the closest.
Right, yeah. It's much better than the Trapezoid Rule and the Midpoint Rule and all the other ones, for sure. Yeah, much better. Okay, so let's label some of this stuff. So let's use this picture since we have it up. x1, x2, x3, x4, x5. Okay, x sub n. Ooh. X sub n. Okay, and then what did we say about n? It has to be, remember, it's very important. Even. Has to be even. Why? Because to interpolate, it has to be in pairs, right? Your steps have to come in pairs to be able to do this. Otherwise, you can't find the parabolas, right? You would be finding half of a parabola, 2 points. That's not okay. That doesn't fit into the framework. Okay. So here, let's do this. I think. All right. So let me label this as y0, y1. Y2, Y3, Y4, Y5, and then so on and so forth, and this is Y sub n. So let me erase this. Hold on, give me a second here. Okay, so what we're going to do is we're going to extend this idea, and notice that if I shift this parabola over, does the area under the curve change? No, right? You're just shifting it. So that's why we did it here in this interval because it's easy, but then you can always shift it around. So, so the integral, okay, the integral of f of x dx from a to b is approximately equal to, so let's write this down. So my first subinterval would be from x sub 0 to where? Okay, so then what would it look like? The first, the first thing that I would add. We just drive it. It's at the bottom. What was it? H over 3. Okay, good. H over 3. And then notice H over 3 is on all of them, right? So is it okay if I factor it out of the entire thing like that, just like we did for the trapezoid rule? Okay, so H over 3, and then we're going to add how many y zeros? 1 y0. How many y? 4 y1s. How many y2s? 1. Okay, so we have y0 plus 4y1 plus y2, right? Okay. And then plus, so now we go on to the next one. So this is 2 to 4, right? Okay, so then at that point, so again, h over 3, right? We took it out. And then what would it be? Y sub 2, 4y sub 3, y sub 4. Does that make sense? So it's 1, 4, 1. And then 1, 4, 1. And then 1, 4, 1. So this is y sub 2 plus 4y sub 3 plus y sub 4 plus, okay, and then what would the last one look like? So we're running out of room here.
Y sub n minus 2.
Y sub n minus 2
Plus 4y n sub n minus 1.
Running out. Okay, so plus 4y to the n minus 1. N minus 1 plus 4y sub n. Just making sure you guys are paying attention. Just making sure you guys aren't asleep. Okay. Then what do you guys notice?
With the exception of the first and last again.
I can simplify this, right? I can simplify it because notice how, so there's a definite pattern, right? This is equal to, so I have the h over 3, right? And then what's going on, how many y sub zeros do you have?
1.
1 y sub 0. How many y sub 1s?
4.
Okay, 4 y sub 1.
2.
But notice you have 2 y sub 2s, right? So this one matches up with that one, and you have 2 y sub 2s. And then how many y sub 3s?
4.
4. Are there any other y sub 3s on any of the other parentheses? So like would the next one have a y sub 3 in it? No, right? It would have, though, a
Y sub 4.
y sub 4. So how many y sub 4s would you have?
2.
2 y sub 4s. And then plus
2 y sub n minus
2 y sub n minus 2, right? Because this one would have one with the one before it, right? This one right here would have one before. And then the next one would be 4y to the
n minus 1.
n minus 1 plus
Y sub n.
1 y sub n. So the pattern goes, you have 1 y sub 0, and then 1 y sub n, and then it always goes 4, 2, 4, 2, 4, 2, 4, 2 in the middle, right? For however many you have. And that's it. That's Simpson's rule. Isn't that awesome? And just think, it's like, wow. Just draw parabolas in between. Forget this straight stuff. So Simpson's rule is pretty cool. There are some other, more fancy ones if you guys are interested. You'd have to take another class, but it's pretty awesome too. Classes. More learning. Learning is great, Learn new things, and I love learning. Do you guys like to learn things?
Yes.
Oh, great. Okay. That's the spirit. Okay. So do you guys want to do an example? No, because it's a numerical approximation. I mean, so really the examples for this are actually pretty boring. I mean, I think because you're essentially plugging numbers into a calculator, you know, and there's no fun in that. What is interesting, though, is telling a computer to do this. Now that is something interesting that I will ponder when I do your next homework assignment. So give me a function that we can't integrate. An example.
Sin x over x.
There you go. That's a good one. Where do you guys want to integrate it from and to?
1 to 5.
1 to 5.
Let's do pi over 2.
Yeah, let's do it in terms of pi. Okay, so pi over 2 to pi. Okay, so let's use... All right, let's see. Okay, so let's do the trapezoid rule. Midpoint, and then let's do Simpsons, and let's not do too many because this becomes very annoying. How many? 3. Well, it can't be 3 because it wouldn't work with Simpsons rule.
Well, it's going to work 4.
4. 2 would be really no fun, so let's do 4. Okay. All right. So the trapezoid rule. So the it depends on how comfortable you are, but what I would say is it's a good idea to draw a number line from one end to the other to figure out your the values that you're going to plug in. So like you're going from pi over 2 to pi, you're breaking it up into 4 pieces. So that's 4 pieces, right? So, and then you can find each one of these, right? So, you know, halfway between pi over 2 and pi, what is that?
3 pi over
3 pi over 4. Okay. And then halfway between pi over 2 and 3 pi over 2 is...
Pi over 8.
Mm-hmm. How many?
5 pi over 8.
Oh, okay. Sorry. I thought I heard something else. 5 pi over 8. And then between
6 pi over 8. 8 pi over
7 pi over 8. Okay. So then the the trapezoid rule. So the area is, let's use the notation that your book uses. I think your book uses. I think they put trapezoid is t sub n, so t sub 4. So what is the trapezoid rule again? Delta x over 2, and then it's
y sub 0 plus
okay, delta x over 2, and then y 0. How many y1s?
2.
2 y1 plus
2 y2.
2y2 plus 2y3 plus y sub 4. Right? So it goes 1 and then 2, 2, 2, 2 until the last one. Right? Okay, so this is equal to, so what is delta x? Delta x is the width of your interval, right? Which is
Pi over 8.
pi over 8. Ooh, wow, okay. All right, so this would be pi over 16, right? And then, all right. So then y sub 0, so that's the value of the function at the first point, right? So you would plug in pi over 2. So sine of pi over 2. Did you guys bring a calculator today?
Yes.
We wouldn't have this 6 as intensity, will we?
No.
Back me up. Go ahead and bust yours out soon.
Okay, so you go through all this stuff. So I'm gonna make you guys do this right now for me. And then plus, so you guys get the drift, right? And then plus sine of pi over pi. So you just evaluate it at each one of these points. And then now maybe we should divide and conquer. One person does this one, the other one does the midpoint. Otherwise, I'm going to leave and you guys are going to be here calculating them still. Notice for the midpoint though, which values would you use? Would you use any of these? You would use none of them, right? All of them would have to be exactly halfway between all of them, right? So if you're doing the midpoint rule, you would have to find completely new values at each one of these. So let me erase this. So you'd have to go halfway for all of these. So halfway, halfway, halfway. And one thing to notice is for the midpoint you would use 4, right? 4, you would evaluate 4 times. Notice for the trapezoid rule, you're actually evaluating the function 5 times. So it's just a little note to self. What would it be halfway between pi over 2 and 5 pi over 8? What would that be?
Pi over 16 and yeah.
9 pi over 16. And then wow.
Yeah.
Oh my god. No, it would be how many? No, it wouldn't be 15. It would be 14, no? Or sorry, 13. Right? 13, right? Because you have, so this will help. This is 4 pi over 8, right? So the length of each step is 1 pi over 8. So from this one to the next one would be pi over 8, or 2 pi over 16, right? Which is actually 11 pi over 16. So no, everybody was wrong. Good job, everybody. Good job, everybody, including me. So you only get one example of these because they're so annoying. Oh my gosh. Okay, so pi over 8 times, and then you evaluated all those points that we just found, right? 9 pi over 16 over 9 pi over 16 plus da-da-da-da-da plus sine of 15 pi over 16 over 15 pi over 16. Okay. So thank you for picking a great problem, Rode. Everybody can thank Rode on. Okay, did you guys get this one?
No.
You guys are still working on this one?
If we go ahead and change the values, we're going to take the 0 to pi and give you a number.
From 0 to pi? But what about from pi over 2 to pi? That's the one we've been doing.
Yeah, still working on
Oh.
Yeah, the calculator's winning.
What is it?
Calculator's winning.
The calculator is winning.
Uh-huh.
that. Do you use the Wolfram?
3, 4, 3, 7.
Do I?
4.
Every once in a while. Why?
Do you know how to change the evaluation? Like because it just gives me a number. That's what I was saying. It spit out the evaluation from 0 to pi, but I don't have to change it from pi over 2.
Oh, you can tell like integral and then from pi over 2 to pi.
Oh, there it is.
Yeah.
Good lord.
But it'll give you, I mean, so if you put it into Wolfram Alpha, it'll give you a much better approximation than what we're doing, which I guess is good to compare. So what about Simpson's rule with 4? Wow. You guys really made me do this, huh?
Absolutely.
This is like torture. It's like torture for me, the worst ever. Okay, so, all right, so I have sine of how many? So if I'm doing Simpson's rule, it would be sine of, oh, okay. What is it?
Switch it into
Like
the
0.0227.
0.000227?
Yeah,
For which one?
For the one I
The first one?
I got 0.481.
Jeez, I got 0.343.
Yeah. Okay, I'm not trusting any of yours. Okay, so if I'm doing Simpson's rule, it would be sine of the first value, right? Pi over 2 over pi over 2 plus
4 times
4, right? Because it goes 1, 4, 2, 4, 2, 4, 2. So 4 sine of
5 pi over 8.
5 pi over 8 over 5 pi over 8. Okay. Plus 2 sine of 3 pi over 4, right? Over 3 pi over 4 plus 4 sine of 7 pi over 8 over 7 pi over 8, and then plus 1 sine, right? I guess actually point close to 0 would make sense, I think. Does it make sense? No. Okay, so what do you guys got for me? Did you guys get anything interesting from your calculators?
This number.
I got the answer to the problem, but not the other.
Okay, what did Wolfram Alpha say?
The actual, I didn't create the rules. I haven't figured that out yet. But the answers will come out was 0.481175.
Okay, so let's use that since Wolfram Alpha uses a much better approximation than any of these. So the closest that we can get is 0.48.
Yeah.
48 what?
481175.
Okay, so 4811. All right, so this is from Wolfram Alpha. Okay, so did any of these come anywhere close? Can anybody give me a reliable answer for this one? That sounds actually pretty close because we didn't use that many steps, right? This is only 4, so it makes sense that it would be off quite a bit. What about the midpoint? Did anybody do the midpoint? Did anybody do Simpsons? I don't think you guys are going to finish in time. Yeah.
What is the graph supposed to look like? Is it the one that's in between 1 over x?
It's the one that, it's the funny function that you look at in Calc 1, remember, where it's,
Squeeze Theorem,
you can use the Squeeze Theorem. Let me find a good spot here. Okay, I'll go down. Okay, so it's this one. And it has a hole right there. So it's the interesting one that you kind of look at in the beginning where, you know, the function isn't defined at 0, but the limit actually, the limit actually exists and it's equal to 1. You probably did it using the Squeeze Theorem. great time. Great times with the squeeze theorem. Do you guys remember that? Do you guys remember the squeeze theorem? You're going to.
remember that word.
You're gonna eventually,
Not give me a-
because it's gonna come
okay,
back.
Simpsons rule, I got 0.890007.
Okay, I'll leave this as a homework assignment for next time for you guys to plug them in properly. But okay, all right. Have a
I dropped a, so probably forgot a parentheses in there somewhere.
have a good night.